Hello everyone, my name is Vihasu Haspar and I'm currently studying in Sri Venkateswara College of Engineering. Today we're going to talk about undisability, a language that is not recursively enumerable. So the topics we're going to talk about today include introduction to recursive enumerable languages, understanding undecidability, languages and recursive enumerability, and case studies and proofs. The first thing we're going to look at is the introduction to recursively enumerable languages. So the formal definition for a recursive enumerable language is that it's a set of strings that can be enumerated by a Turing machine. It accepts all strings in the language. So this is the formal definition. Few of its properties and an example is given here. So the properties include closure under union and intersection. Example include the set of valid computer programs in certain diaphragm equations, etc. Next, we're going to see the importance of computability theory. So, what is the importance of this in the computability theory? First is in Turing machines. So, Turing machines are theoretical models that define computability, central to understanding recursively enumerable languages. Next is Church-Turing thesis. So, this thesis persists that any function computable by an algorithm can be computed by a Turing machine, underlying the significance of these languages. Next, we're going to talk about the applications. So, applications extend to computer science fields like algorithm design, language processing, and complexity theory, illustrating practical relevance. The second part is understanding undecisibility. Now, what is the decision problems? What is the concept of decisability? So, in computer science, decision problems are questions with yes or no answers. These are used to determine the solvability of various computational tasks. So these expect straightforward answers for the problems. Next is decidable versus undecidable problems. So what are decidable problems? They usually have an algorithmic solution that always provides a correct yes or no answer. Whereas an undecidable problem is something which does not have a proper yes or no answer to it. So ones that cannot be algorithmically solved. So, how do we prove undecidability? What are the techniques with which or methods with which we can prove this? So, the first is reduction techniques. So, reduction is a technique where one problem is transformed into another to prove the second problem's complexity, often used to show undecisibility. So, this can be an example of conversion of a problem from one state to another state. Next is diagonalization method. So, diagonalization method constructs a problem by ensuring any proposed solution fails at some point. So, demonstrating the problem's undecidability again. Next is the halting problem. The halting problem is a classic example of undecidability, proving that no algorithm can universally determine if a program halts or runs indefinitely. Next, we're going to see the languages and recursive enumerability. First is the definition. Again, like I said before, recursive enumerability languages are those for which a Turing machine can enumerate all valid strings. They may not be decidable, but have an enumerator. Examples for these include the halting problem, the context-sensitive languages, which can be recognized but not necessarily decided by a Turing machine. A significance for this is that these languages are important in theoretical computer science as they help understand limitations of algorithm computations and decidability. Next, we are going to see what is non-recursively enumerable languages. Again, non-recursively enumerable languages cannot be listed by any Turing machines. They are not enumerable and have even stricter limitations than undecidable languages. The digital diagonal language. The diagonal language is a classic example of non-recursively enumerable language constructed using digitalization to show it cannot be recognized by any Turing machine. So, what are the implications of non-recursive enumerable languages? The existence of these languages reveals fundamental limitations in computation, showing there are problems no algorithm can ever solve or even enumerate all solutions to. Next is a few case studies and proofs. So the first is the halting problem. So what the problem statement was is the detailed description about this title, about 20 to 30 words. The halting problem asks whether a given program will halt or run indefinitely based on its input, crucial in demonstrating limits of computation. So you might have asked for a detailed description but you have given about it into 20 to 30 words. So if the detailed description that you require is longer than that, you will have to see if the computer will actually stop at 20 to 30 words or if it will go on indefinitely till it achieves the goal of the problem statement. Next is proof of undisability. So detailed description about this title, about 20 to 30 words, Alan, turning proved the halting program indecipherable, meaning no algorithm can universally determine if program halts, emphasizing compatibility boundaries. Next, we're going to see at other undecipherable problems, post correspondence problem. First is detailed description about this title, about 20 to 30 words. The post correspondence problems involves matching list of strings. It was proven to be undecipherable, highlighting critical insights into the computational theory. Next was Hilbert's 10th problem. So, detailed description about this title, about 20 to 30 words. Hilbert's 10th problem asks for an algorithm to determine integer solutions to polynomial equations, proven undecidable again, as it shows profound mathematical computation limits. Next is interpretations and consequences. Detailed description about this title, about 20 to 30 words, undecipherable problems, such as those listed, reveal fundamental limitations within algorithms, informing fields from theoretical computer science to practical software development. Thank you so much. Have a great day. Hope you enjoyed the presentation.